Section 4, union probability and mutually exclusive and non-exclusive events. So before we start, just want to mention that when you see this U symbol, it stands for the union, or the word or. And when we see the upside down U, this is the intersection, known as the and. Okay, so picking a card from a standard deck of 52 cards, we have 13 hearts, 13 diamonds, 13 clubs, and 13 spades. So let's go down the inclusive side. So if something is inclusive, then these events have a common intersection point. So the probability of A plus B together, you have to then subtract the intersection of both of those things. So let's look at an example. So things that are inclusive are going to be, let's just talk about some real world examples. So one would be like people who live in Maryland, and then people who also attend the University of Maryland College Park. So you could have people live in Maryland permanently, but then also go to College Park. Or you could have someone who lives in Maryland who doesn't go, or someone who doesn't live in Maryland that goes. So if you want to find the probability of a person who lives in Maryland and goes to College Park, you need to add both of those together, but then you need to subtract the overlapping intersection parts. So the reason why you want to subtract it is because you don't want to count those same people who live in Maryland and go to College Park twice. So let's look at these examples. So for example, we have a probability of a heart or an 8. Well, we can have, if we drew a Venn diagram, we can have all the hearts on one side and the 8s on the other. And then right here, this intersection point is going to be the 8 of hearts. So you can have a card that is both an 8 and a heart. So we need to subtract it so that we don't double count it. So the probability of a heart is going to be 13 over 52, plus probability of pulling an 8 is 4 out of 52. But then we need to subtract that one overlapping card to make sure we don't count it twice. And when we do this, we get 16 over 52, which simplifies into 4 over 13. Okay, so the next example says picking a jack or not a spade. So then we're going to do the probability of jack, probability of not a spade, and then we're going to subtract any jacks that aren't spades. So probability of choosing a jack is 4 out of 52. Not a spade is everything other than a spade, so you have 39 options, 3 suits out of 52. And then you have to subtract if it's a jack and not a spade, so therefore clubs, diamonds, and hearts, so you have 3 out of 52, which gives us 40 out of 52, which simplifies to 10 out of 13. Okay, and then I'm going to squeeze on the bottom probability of a club or a face card. So this is a club plus a face card, and then we're going to subtract any clubs that are face cards. So the probability of getting a club is 13 out of 52, plus a face card, there's 12 face cards. And then a club that is a face card, there are 3 clubs, Jack, Queen, King, that are face cards. So we're going to subtract 3, and we get 22 over 52, which simplifies to 11 over 26. Okay, mutually exclusive events, things that don't have a common intersection point. So heads and tails. You can't get heads and tails. You can't turn left and right in a car. They have nothing to do with one another. So all you need to do is just add the probabilities together. So for number 2, probability of a red or an ace of spades. Well, an ace of spades is not red, so they're separate events, exclusive. Probability of a red card is 26 out of 52. And then probability of the ace of spades is 1 out of 52. So my probability is 27 out of 52. And then a 2 or a queen, completely different cards, so not even related. Probability of getting a 2 is 4 out of 52. And same for the queen. There's 4 queens out of 52. So we get 8 out of 52, which simplifies into 2 over 13. All right, so part 5 talks about dependent and independent events. So let's look at dependent events first. We have the outcome of the first event affects the outcome of the second. So I have a jar of candy bars, and it's a Hershey's and a Twix and a Reese's. Well, the probability of picking the Reese's changes if the first person who picks one gets the Reese's. Now my probability for what I have to choose is affected because now there's only 2 candy bars left. So in this scenario, we have a jar of 10 slips of paper, numbered 1 through 10, and 2 slips are pulled one at a time. So out of those 2, what's the probability of choosing the 5 first and then the number 8? Okay, so this is the equation up here that we're going to work with. This second part is conditional, is the conditional probability. That is how we represent it. So basically it's saying the probability of B given that A has already occurred. So that's what that kind of line in between B and A represent. So the probability of choosing a 5 is 1 out of 10. But then, so now we need to do AND, which is multiplication. I'll use the dot. We're doing AND because this needs to happen next also. I'm not just asking for one thing, I'm asking for a 5 and then an 8. So then an 8 is still 1 card, but now that we chose the 5, we have 9 left. So that probability is going to equal 1 over 90. Okay, so what's the probability of an odd followed by an even? Well, an odd, there are 5 odd cards, or numbers, 1 through 10, out of 10, and then followed by an even. There are 5 separate even ones, but we still have 9 left because we chose an odd first. So this gives us 25 over 90, which does simplify into 5 over 8. Okay, so when there are completely different or independent events, so a coin is flipped, what I flipped the first time has no effect on what I did the second time. So for 2 coins, what's the probability of flipping 2 tails? Well, to get a tails, you have a 1 out of 2 odds, and then flip it again, the same odds. So it's 1/4. And then what if you flipped it 4 times and try to get heads? Well, each is separate. So it's 1 out of 2 to get a heads. So to get it 4 times, you just multiply it. 1 over 2 to the 4th, which is 1 over 16. Now, just so you know, independent and dependent events doesn't have to be just 2 happening like we saw in problem 4. You can have more than that. Okay, and the last section of 14.2 is probability with data. So this chart represents 500 international students that are enrolled in Maryland universities. So if one out of all of these students, if one was chosen, what is the probability that a Chinese student goes to UMBC? So this is asking for an intersection point because we're talking about Chinese students and then also UMBC. So that intersection is right here. So we have 272 divided by 5,000. Okay, so then it's being Chinese or going to UMBC. So being Chinese, this is that total, or here, let me draw it again. So this is the China row. So if you're Chinese, 2,791 out of 5,000 is the probability. And then UMBC is 516. And we're going to add them because it's or. However, these are inclusive events. They have an overlapping part right here, that 272 we just found out. So what we have to do, since you can tell with the way that I circled in the chart, I counted 272 twice. So I need to subtract 272 to make sure I just count that value one time. And when I do that, I get 3,035 over 5,000. Okay, and then the events of being Nigerian or Saudi Arabian. Well, those are two separate things that we're talking about. So they're completely separate. There's no overlap. Completely different nationalities. So if you were Nigerian, it'd be 288 over 5,000 plus, because it says or, 254 for Saudi Arabian. Now, I don't have to subtract anything because these are completely different events. These are exclusive, meaning we just take them and we add them together, and our answer is 542 over 5,000. And notice when I circled those rows, there was no overlap. And the final thing that we need to find the probability for is an international student in Maryland. Well, right here, 5,000 international students in Maryland out of 5,000. All of these are international students in Maryland. It doesn't say anything about College Park, just in Maryland in general. So that probability is 1.